Welcome. I want to say something more about the spectrum of the Hodge Laplacian. So here are the definition. We have some topology. We have a finite abstract simplicial complex, and it comes with a natural topology, finite topology generated by the stars, and it's non-Hausdorff. And we have closed sets, we have open sets. For each of these sets we have then also exterior derivative of both for the open sets and the closed set, and so we have a Laplacian. Dirac operator squared gives us the Laplacian, and so we have a spectrum which we can associate to each closed set, each open set. And the Hodge Laplacian comes in blocks, and each of these blocks have a spectrum, and the zero eigenvalues, the number of zero eigenvalues in each block, this is the Betti. These are the Betti numbers, and this gives a Betti vector. So we have a Betti vector attached to the open sets, we have a Betti vector attached to the closed sets, and we have a Betti vector, of course, attached to the whole set, which is last time I mentioned that there is no general inequality between the spectra, and I actually was fooled by just looking at things in the wrong way. So let's look again at this Ghostbuster complex. I like this case where we have the G has an additional connection here. If we take it away, the Betti vector has decreased by 1 in the second entry here. E1 has decreased, and what happens is that we actually have just added, and we go from here to here, we add an open set. So the interval itself, which we have here, this set here is alone. This is actually a star. This is an open set. So we have added an open set. We have taken this closed set, this open set, we got the whole complex. And I was interested now since many weeks about this relation between the Betti vectors of K and U and G. And so sometimes we have equality. I often saw that there is equality, especially for manifolds. And then there is also cases where we have inequalities. So in this case we have a equality, so they add up. The Betti vector of the circle plus the Betti vector of this interval here has this actually has a Hodge Laplacian, which is just a 1 times 1 matrix, zero matrix. Now I was looking at the spectrum and I said, okay, because there is a one eigenvalue 0 more here, there cannot be an inequality, but I was padding the eigenvalues in the wrong way. You have to pad the eigenvalues to the left. So if you pad the eigenvalues to the left, you add just zeros, smallest elements to the left, then you get the same number of eigenvalues, and then you can compare them. And what I just realized last week, that there is always a inequality here. So when you take a closed subset, so subsimplicial complex, and you look at the eigenvalues, they're always smaller or equal than the eigenvalues of G, and also for the open sets. Now this is a result which is known in the graph case, in the case when we have a one-dimensional simplicial complex and you only look at the zero form Laplacian, which is the Kirchhoff matrix. And then there is also a one-form Laplacian, which is essentially isospectral. But this is now in general, indeed also you can restrict yourself to the K-forms, and you have this inequality on each K-form Laplacian. Really cool. And actually the proof is essentially the same than in the Kirchhoff Laplacian case. We will come to that, but so we have seen that actually last week. So this is this well-known result for the Kirchhoff Laplacian. This is a generalization of this result. Actually, I was interested in this inequality here. If you add the eigenvalues up from the open set, which is the environment, and the closed set, which is the laboratory, you should get a total energy which is smaller or equal than the whole thing, because the whole thing is more connected. So that was the intuition, but that's not always true. It's almost always true. So there are very, very, very few cases where it is false. You have to search through many examples to find an example where this is not true. And I mentioned last time that one can actually enforce it to be true by taking this Witten coordinate deformation, where you just focus, you kind of put your microscope in the right place, in the place where the things interact, and then you can force it. And actually one can understand this pretty well when you do a Morse build-up of your simplicial complex. So what you do is, when you write down the simplicial complex, you order the sets according to lexicographic order, and then what you can do is, if you take the last element away, that's actually, when you take the last element away, the last element is locally maxima, meaning that there is no other set above it. So if you take this set away, then you can look what happens with Betti vectors, and you can look what happens with also number of critical points, and then you get actually directly to the strong Morse inequalities, which are pretty cool. Actually, that's one of the points of Witten deformation, was to get to the strong Morse inequalities. In the continuum here, it's essentially obvious from the build-up, from this CW Morse build-up. So a CW structure gives you a little bit more information on the simplicial complex than the simplicial complex itself. So there are many CW structures. So I have here a complex, and so this is G. And what I can do in order to build it up, I take a locally maximal element. So one of the locally maximal element, for example, would be this triangle. I can take this away, so I get a new complex. But what happened is the cohomology of the Betti number, of the first Betti number, has changed, and we have a hole here. If I take away this triangle, I have got the hole. So what happened is, in this case, I actually have added. So when I go from, I went from here to here, so I added some cohomology in the one lower. Or what also can happen is, so I can do that also here. If I take this maximal element away, so I have just still the vertex here. So in this case also we have just taken away, we have just added B1 element to B0. Now this guy here is locally maximal. I can take this away. When I take this away, I just remove the B0 by 1. So there is a dichotomy. There are two possibilities. Either we add, and when we extend it, we either add 1 to the cohomology of which belongs to the dimension of the element. Like, for example, if I add a new 0-dimensional part, I add 1 to B0, or I remove 1 from the for example, if I do that and then I add this additional thing, I have just closed that additional B0, removed that additional number. So the Euler characteristic would be if you just add up everything until the BD, but if you just stop the inequality. The CK are the number of critical points. This function, in this case of this function, the Morse inequalities are pretty clear. But the point of the Morse inequality are true in general when you have a Morse function. And one can define Morse functions also in the discrete. But I just mentioned this because in the proof, when you're looking at the proof here, when you actually do that, what you need only to understand is what happens if you take away a maximal element. So if you go from a complex to a subcomplex, you can do that by removing maximal elements. That's this remark here, and that actually allows us then just to study only the spectrum, what happens with the spectrum when you just add 1 element to the simplicial complex, 1 open set. So you attach 1 small open set, which is the star of a locally maximal element. So this is what actually happens. Then the matrices are just getting extended by 1. So especially this Dirac matrix gets extended by 1. And one of the things you can do, for example, you can use the interlace theorem to see that the spectrum has now to be interlaced. And that's the spectrum of the square root of L, right? D square is equal to L. And then you see that the spectrum satisfies this monotonicity. One can also go with this proof, which see, for example, in Spielmann's notes, when you just notice that this is when K is a subcomplex of G. In this kind of special case here, you have this Lerner partial order thing. So the difference is a positive semi-definite matrix. And one way to see this is using the Courant-Fisher. You can write the eigenvalues as a minimax. Minimize overall vector subspaces of dimension k, and you take the maximal here. And that you can write, you can take the L as d square, you can take the d on the other side. So this is length of the vector dv. And what happens if you just add one new row and one new column, what happens is this is just, it can only get bigger. So that's the argument which was in the Kirchhoff case, goes also over here, just using the fact that L is d square. But this is by itself is pretty cool. So we have a monotonicity of the eigenvalues of the Hodge Laplacian in general for any simplicial complex, which is pretty cool. Okay, that's it for today.